Welcome to the lecture number 19. So, in the last lecture we are discussing about the detector of this TCSPC system. So, as I said that the ideal requirement is that constant gain of this detector and the perfect response time. I have already discussed about the constant gain. Now, I will discuss about this response time of the detector. So, to do that, let me consider that the light, the photon, when interacted this photocathode, the time is time t equal to t0. So, that this time is time t equal to t0, and the whole process starting from here, all this electron multiplication, all this, all this complete process, right. Obviously, this is not instantaneous, I said. So, this process let us say is will take a time t t. This is the total time taken for this process. Okay. So, here, right, at what time this electron pulse will come out? At time t equal to t0 plus tt. But it is no problem for me, because I will simply add this tt during my time measurement, no problem at all. But now, if this photon is falling, because these photocathodes having some dimension, this is the dimension of this photocathode. See here, this is the dimension of my photocathode. This is the dimension of my photocathode. So, the photon may fall at this position as shown here, but it may also fall at this position, because it has some dimension. If it falls on that particular position, then this ejected electron will be directed around this position of this first dionode, then this will be directed like this way, which will be directed like this way, and then all these things, which you can immediately figure it out from this diagram, that the path travelled for this red one and the path travelled for this yellow one, they may be different, may be same, it is true, but may be different, and in most of the cases it will be different. That means, whatever I said, this Tt is not a constant value. Whatever I said, this Tt is not a constant value. That means, I have a spread in transit time, that is called the TTS. I have the transit time spread. Which I am trying to show you in this slide. Suppose this is my electron pulse, which supposed to come at t0, right, but because of this transit time of the PMT, because of this transit time, I am going to get this at time t. Okay. But this is not a constant, right. This is not a constant, because this width may vary, right. So, sometime I will get at this position, sometime I will get at this position, and so on, right. So, this is called the transit time spread, and this transit time spread, so here I have written that, and this transit time spread is the most difficult part of this kind of detectors, right. I want to measure the arrival time of the photon. If you remember our TCSPC system, in the TCSPC system, I want to measure the arrival time of the photon. The photon arrived here, and it took some time for the conversion, then the electron pulse will go and tell that stopwatch, my tach, that okay, now I got a photon, so you stop counting, right. So, when I have, okay, let's describe it once again over here. So, here when the laser has excited your sample, in this case it send one signal that you start the counting the time, and then there is emission of photon from the sample, and then the first emission photon is being detected by this detector. This detector will send the signal, okay, now I got a photon, so you stop counting, and then that is the time between the excitation and the emission of a photon, right. And we plot such kind of event millions and million times to get the histogram, right, you remember. Now in this case what will happen, that from the excitation and the detection of the photon there will be a time error, and the time error is originating from this transit time spread, as I explained in the last class. But this value of the transit time spread, if it is small like 1 picosecond, 2 picosecond, then I have no problem, because I am going to measure a lifetime of nanosecond. If there is error of 1 picosecond like a 1 by 1000, then who cares, nobody will care. But unfortunately for normal detector, the value of this transit time spread is really high, is about 500 picosecond, 1 nanosecond. If the detector quality is bad, then it could be 1 nanosecond is the transit time spread. That means you are going to measure 1 nanosecond lifetime and your error in the measurement is 1 nanosecond, then you are no here, you cannot do the measurement properly. So there are a lot of development for this, because this is the heart of this instrument, right, is the detector. So detector is detecting the photon and it is converting to the electron pulse, and that is used to stop the counter, my tag. So there should be no error in this case, otherwise whatever the error will be present, that error will be reflected in the lifetime measurement. So I want to minimize the time measurement error in this case. So for the normal PMT, that error is about, as I said, 500 to 1000 picosecond, and you cannot use such kind of detector to measure a lifetime of 1 nanosecond, right. If the lifetime is 10 nanosecond, 20 nanosecond, 30 nanosecond, then it is okay, then no problem. But if it is less than 1 nanosecond, then it is impossible for you to measure. And there is a lot of development how to reduce this transit time spread from this then, and people have ultimately come up with a better PMT, better detector, where the transit time spread could be 10 to 25 picosecond, and nowadays people are using such kind of detector. But what about if I want a detector whose transit time spread is less than that, 10 or 25 picosecond? There is no such kind of detector available in this world. The minimum time that transit time spread could be achieved like about 10 picosecond. You cannot go beyond the 10 picosecond. That means if you want a measurement of a fluorescence lifetime, that lifetime is 1 picosecond. If just consider that lifetime is 1 picosecond, with this kind of setup you will not be able to measure it. You have to go for another setup, and that is why I told you earlier that I am going to discuss two setup. One is the TCSPC, which is widely used, and the another is the fluorescence upconversion. The fluorescence of the principle of fluorescence upconversion is completely different than this TCSPC, and in that case you will be able to, although the detector will be same, but still you will be able to measure the fluorescence lifetime of 1 picosecond or something like that with this same detector, because the principle is completely different. We are going to discuss that later. Okay, coming back to this detector of this TCSPC. So as you have understood that this transit time spread is one of the important issue, and if you want to measure this lifetime with a better resolution, then you have to go for a better detector where the transit time spread is small. Right. Another thing which I already said on the last day is that constant gain. Let me show you this with this diagram. So I said that the detector, they do not have this constant gain. That means if one photon falls, sometime 1 lakh electrons will be ejected, sometime 95,000, sometime 110,000 electron will be ejected, and so on. So there is a amplitude jitter, the signal will sometimes small, sometimes large, sometimes small, and so on and so forth. Now, you also have this noise that I already talked about during the absorption spectrophotometer, that all the detectors has a thermal noise. Even the photon will not form, the detector will give you some signal. Those are simply the thermal noise. So, these are the, let us say, the thermal noise. So, if I want to get the timing of the arrival of the photon, then I should not detect these signals because these are the noise. So, what I should do? I should put a threshold electronically over here and say that if this signal is more than this noise, then those are my signal, otherwise they are not signal, those are noise. I am not going to consider those as a signal. Now, you see that when I put this kind of threshold over here, right, and I am just showing it over here by a Gaussian type of pulse. So, I am now putting this threshold over here. So, here in this axis, this is my start time of this signal, the big signal, and this is the start time of this small signal. You remember here that both of these pulse, this is, let us say, this is, I am writing it like that way, this is the electric pulse from detector due to photon number 1. This is the electric pulse from the detector due to photon number 2, and I consider here that photon number 1 and number 2, the arrival time, arrival time of photon number 1 and number 2 are exactly same. I consider this. Okay. So, when they arrived exactly at the same time, now I am not considering this transit time spread, I am considering that amplitude of this signal, right, because they have a variable gain. So, in this case, for the photon number 1, the gain was more than the photon number 2. So, I got a bigger signal for photon number 1 here, bigger signal, and I got a small signal in the case of photon number 2, right. So, this is number 1 and this is for number 2. So, if they arrived at the same time, then these two signal should reach the detector exactly at the same time, but because of this threshold and because of this cutting, you see the start time of the signal is here and the start time of this signal is here. So, this is for the number 1 and this one is for number 2. So, their arrival time to the detector, the arrival time of the signal due to photon 1 and photon 2, right, they are different, arrival time are different, and this is a big problem. Although these two photons arrived at the same time, but they arrived at the same time to the photocathode, but their arrival time to the stopwatch, the signal arrival time to the stopwatch are different. This is known as, no, I have written here, pulse height induced timing jitter. There is a timing jitter, right, or is also known as time jitter induced by the amplitude jitter. Of the detector. So, we have problem over here. How to solve this problem? and this time is a big time gap, is not small, is about 200, 300 picosecond, sometime 500 picosecond, that means comparable to your lifetime measurements. So, if you do not take this problem seriously, then your lifetime measurement will be too much erroneous, right. So, I have to somehow solve this problem, and the way to solve this problem is introduction of the CFD just after the PMT. Let me show you over here. The CFD is a device, is an electronic device, right, is a device by which I can reduce this difference in time to a smaller value. It cannot be 0, but it can be reduced significantly. So, just I have done a simple thing to show you the function of the CFD. In the CFD, like after this threshold, I got the two pulse, one arrival time is here, the second arrival time is over here. So, let us take this first one, the bigger pulse, the number 1, this is number 1. I took this number 1 over here, and I have divided this number 1 in two different pulse. One is 66%, here they see the amplitude is 1.5. Now, I have made it 1 and another is 0.5. The smaller one is inverted and shifted in time at your desire, and then these two you sum up. If you sum up these two, what you will going to see? You will see such kind of profile, right, as shown here. Hope you will be able to see. So, this kind of profile, like this kind of profile. For the smaller one, you do the same thing. You divide this as 1/3, 2/3. The 2/3 is over here. This is for number 2. So, this is 2/3 of number 2. This is 1/3 of number 2 inverted, shift at the same time, and then you sum it up and you will see this curve, right, as I showed here, this curve. And now you see when these two pulse will get a positive value, the time difference is less than the time difference which was present originally. So, in this case, by using this kind of CFD, I can reduce that time jitter induced by the amplitude jitter of the detector, and the full form of CFD is constant fraction discriminator. Okay. Okay, so now let us discuss about this time to amplitude converter tag. So, as I said earlier that this is a kind of stopwatch, but is actually is based on the capacitor, right. So, it generates a voltage proportional to the time between the start pulse and the stop pulse. Right. So, when it comes as a start pulse, so the voltage will keep on generate, it will be charging, and once there is a stop, so it measures this voltage, and there is a calibration that how much voltage can be generated with how much of time. So, with this calibration, like typically 0 to 10 volt can be generated with several nanosecond to microsecond time region. So, I can divide that per millivolt is how much time, and that will be used for the measurement of the time, like it will behave like a stopwatch. Okay, so, with this what we understood till now is this setup. So, I have a laser, it excites the sample, the desired emission wavelength is selected by this monochromator, and then this photon, the first detected photon is detected by this PMT. So, here note that here the first arrived photon, which not necessarily the first emitted photon. That is the heart of this TCSPC. If it is like that, then there is a no decay. Always I will get one count or several counts on the very first few time regions. So, I will never get the count in the later time. So, I will never be able to reproduce the decay profile in the histogram. So, note that. So, not always the first emitted photon is the first arrived photon, that means the first detected photon. Okay, so, it is detected, and now detector has amplitude jitter, which will going to give you the time jitter, and that is rectified by the CFD over here, constant fraction discriminator, and detector is also having the transit time spread, which obviously cannot do anything. You cannot, only have to buy a better detector where the transit time spread is small, right. And then it will use as a stop here. But here you notice here that I have just changed that start and stop like this way. I have written here is stop and here is start. So, it is the correct one, right. This is the wrong one. Let me explain it. So, the reset time of this stack is about millisecond, and I said that the detection is very small rate, because I have to ensure the first emitted or first arrived photon should not be always the first emitted photon from the sample. This is important. To ensure that, what I said, that I will reduce the detection rate to 2% or less than 2%, so that the photon, the first photon which is emitted like here, it will go to some other direction, it will not going to the detector if my detector is present here. So, the first emitted photon may go this way, the 10th emitted photon may come like this way, right. So, the photon which is emitted at much later time, if you find a possibility that this will come towards the detector, then the detection rate should be very low. That is the important part in the TC-SPC system. So, in that case, as I said, that the detection efficiency is generally reduced to 1%, 2%. That means, for every 100 excitation, I am going to detect only one photon, right. That means, you are going to excite, you are going to start the stopwatch, the tack 100 times, but you are going to stop it only once. That will going to give me the overloading of the tack, and the tack reset time is also very slow, right. So, better if I can use the emitted photon as the start and the excitation as the stop, then only when there is a emitted photon, then the stopwatch will start, and then eventually it will be turned off, right. So, in that case, I have it like this way. This one is actually starting that tack, but there could be some problem related to that this signal will come early than this signal. That is why I have a delay here, electronic delay, that somehow it delayed, so that this signal is coming first and this signal will coming later. So, then the histogram will looks just a mirror image of what I showed. In this case, the histogram is like this. In this case, the histogram will looks like this, right. Okay, let me finish here, and we will see that if some other topic should be discussed on this TC-SPC setup. Otherwise, we will start the fluorescence upconversion on the next class. Thank you very much.